So let's go ahead and find a formula for the sum of the first n odd numbers. So we can go ahead and establish a sequence of odd numbers. So let's go ahead and define a sub n. Okay, so we have 1, 3, 5, 7, 9, 11, and so on. Okay. Now, S sub n is going to consist of the sequence of partial sums. So the first is 1, okay, and then 1 plus 3 is 4, 1 plus 3 plus 5 is 9, plus 7, 16, plus 9, 25, plus 11, 36, and so on. Okay, now you might see where this is already developing here. We're going to go through this a little bit more rigorously. So to get from 4 to 4 from 1, you add 3, obviously. Here you add 5, 7, 9, 11. Let's go ahead and just populate that line. And then we can see that to get from 5 to 5 from 3, you must add 2. To get to 7 from 5, you must add 2. To get to 9 from 7, you must add 2. And to get to 11 from 9, you must also add 2. So we have this constant second difference. Okay. Now, if anyone's taken real analysis, you'll realize that the constant second difference is indicative of a quadratic relationship. So, constant second difference, okay, means, okay, a quadratic relationship. Okay. A constant second difference. Okay. So good. And that we can generally define as S sub n equals an squared plus bn plus c. Of course, n here has to be a positive integer. We can treat it like just like we would a quadratic, a continuous quadratic function. But this is an important stipulation here for when all is said and done. Okay, so if I plug in 1, I should get out 1. If I plug in 2, I should get out 4, since 4 is the second partial sum. If I plug in 3, I should get 9, since 9 is the third partial sum. If I plug in 4, 16, 5, 25, 6, 36, etc. So we can all see what's happening here, but we're going to use this as a kind of as a stepping stone to understanding how to construct these statements based on these differences, these constant differences. In this case, we have a constant second difference. We don't have a constant first difference. We've got a constant second difference. So again, plug in 1, out comes 1. Okay, so a times 1 squared plus b times 1 plus c equals 1. Plug in 2, get out 4. So a times 2 squared plus b times 2 plus c equals 4. Plug in 3, out should come 9. So you got a times 3 squared plus b times 3 plus c equals 9. Okay. Let's go ahead and solve this system. Shouldn't be too bad. Notice that I'm going with 3 sets of inputs and outputs because I have basically 3 unknowns, a, b, and c. So here we go, simplifying. A plus b plus c equals 1. 4a plus 2b plus c equals 4. 9a plus 3b plus c equals 9. Okay, good. I'm going to go ahead and solve for c for everything, and this will be quite easy, in fact. Okay, so solving for c for everything, I got c equals 1 minus a minus b. I've got c equals 4 minus 4a minus 2b. And I've got c equals 9 minus 9a minus 3b. Now, I can go ahead and set c equal to c here, and c equal to c here. It's going to eliminate c, and I'm going to have 2 equations with 2 unknowns, a and b. Let's go ahead and do that. So this is going to simplify our system. So c equals c after all, so I can say 1 minus a minus b is equal to 4 minus 4a minus 2b Moreover, I can say, setting the middle equal to the bottom, 4 minus 4a minus 2b is equal to 9 minus 9a minus 3b. Okay, let's go ahead and get this in standard form. Going to add 4a to both sides. Negative a plus 4a is 3a. Let's add 2b to both sides. Negative b plus 2b is b. And let's subtract 1 from both sides. Okay. Again, down here adding 9a to both sides. Negative 4a plus 9a is 5a. Negative 2b plus 3b is b. And subtracting 4 from both sides, 9 minus 4 is 5. Okay, checking that very quickly. Yes, top equation is right. Bottom equation is right. So we're going to subtract using elimination. We're going to have negative 2a equals 3 minus 5, negative 2. That means obviously a equals positive 1. Okay, now knowing that a equals 1, we can plug in to find b. So we have 3 times 1 plus b equals 3. Well, that means obviously b equals 0. Okay, and now that we know that a and b are 1 and 0 respectively, we can find our c. Okay, maybe zooming out one step here, we've got c equals, we're going to use this top equation, 1 minus a, which we've discovered as 1, minus b, which we've discovered as 0. Well, 0 is insignificant, and 1 minus 1 is 0, so c is 0. Okay, therefore, we found an equation. S of n is equal to 1 times n squared plus 0 times n plus 0 times c, or 0, sorry. Okay, well, obviously the whole thing is equal to n squared, which is kind of what we could have inferred all along. I mean, this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, so on and so forth. So we found the formula for the sum of the first n odd numbers. Pretty easy to do this. Basically, this is I'm using kind of like a reverse mathematical induction technique, and I do want to use this technique going forward. We're going to make a couple other videos finding the sum of the first n even numbers, some of the first n natural numbers, some of the first n perfect squares, some of the first n perfect cubes, and then taking a look at the Bernoulli numbers, which is a kind of a pattern of patterns, as it were, of those constants that remain. Anyway, we love mathematics around here. We love physics. We're going to prove anything you submit to us. Might take us a little time because life gets busy, and as you know, we've got a host of responsibilities up and down, but hopefully you found this video helpful. Please leave a comment if you so choose, and we will see you in the next video.